Good morning, everyone. How are y'all doing today? Good? Good? Does anyone have, ooh, that's too much. Does anyone have any questions before we get started? Can everyone in the back hear me? Is it okay? All right. Does anyone have any questions? Okay. Oh yeah, what's up? Yeah, so the exam grading session is tonight. So your exam grades will be posted tonight. The answer key will be posted tonight. So then you will get them in recitation this week. So you need to actually go to recitation. You'll get them from your TAs. That is also when, if you want to submit a regrade, that's the time that you will do that as well. Is you will look over the exam, you'll discuss with your TA if there are any questions that you think were wrong, because we are not perfect. We sometimes make mistakes, especially with math. Double check our addition. Apparently, as soon as we get to this level, we forget how to use basic calculator functions. So definitely double check our math, because that seems to be where most of our errors come every year. But yeah, if there are any issues, you can submit a regrade request during recitation. Does anyone have any other questions? Yeah. Yeah, so if you aren't able to attend recitation this week, then you can request a regrade later. So the exams become ineligible for regrade the second that they leave a TA or my own supervision, basically. So as soon as you walk away with the exam out of recitation, it is no longer eligible. If the exam stays with the TA, then it remains eligible for regrade until reading day. So please pick it up before reading day, but it can, as long as it doesn't leave the TA's possession, then it's still eligible for regrade. The concern is that there have been questionable issues in the past where it has looked like students have tried to change answers and then submit it for a regrade after the fact. So now, because of that, we just have to make sure that everything is done. One, you have to use pen. So if you make any markings on your exam during the regrade period, it has to be done in pen. That way, again, that way you can't modify the exam after the fact. But yes, it can be done afterwards. And if you aren't able to attend recitation this week, it'll be on you to find a time to meet with the TA to get the exams back. So basically, you'll just have to coordinate with the TA whenever it's convenient for them, whether it is the next week's recitation or office hours or whatever, then you can get it back then. And if you want to meet with me before you submit an exam for regrade, that's also totally fine. So, or if you just want to meet with me in general. If you think that you might want the exam to be regraded, but you also want to meet with me first, just make sure that you leave the exam with the TA and tell them that that is the desire. So that way the TA knows to give me the exam, and then you should email me with your availability so that we can find a time to meet. Cool. Any other questions about exam? The full regrade policy is on our Canvas page, but any other questions before we get started? All right, cool. So we left off with this big picture of what are we going to do all semester. And so the idea was what has electrons, what doesn't, make them meet, make sure you don't violate octets, and then reassess. So that was it, was just go from what has electrons to what doesn't, and make sure that you don't violate any octets. And that is going to work for pretty much every reaction. If you can do that process, although it's a little bit slower, it will get you to the right answer. Thinking through the mechanism will always get you to the right answer. So some of the tips that we had to remember is make sure that your curved arrows, you're paying attention to the bonds that are being made and broken. So when you're going from an atom to an atom, that is making a bond. When your curved arrow starts at a bond, then that's breaking the bond, because then you're taking the electrons and putting them somewhere else. Also, number your carbons. So I had said that a lot of students will frequently lose points because they just have the wrong number of atoms, and that is so common. So make sure that you number your carbons, number your atoms, to make sure that you just The elements that you start with are the elements that you end with. That's the idea. Then we're also going to consider our stereochemistry. So we're not going to forget chapter 5. We're still going to involve are we going R to S, S to R? Are we making a racemic mixture? We're going to pay attention to our stereochemistry. Some additional tips are making sure that we are only moving curved arrows or only moving electrons with our curved arrows. So a lot of students will make the mistake of they'll try to show atom movement with the curved arrow. That is incorrect. Curved arrows show the flow of electrons. Atoms move as a result of that. So your curved arrow is showing the movement of electrons, the flow of electrons. Resonance is going to help explain a lot of observed reactivity. So you want to make sure you're really good at resonance. Almost everything can be discussed in terms of acid-base and nucleophile electrophile. Anything that can't will be oxidant reductant, will be the third category. Most of our reactions occur directly at or adjacent to our functional groups. That's why it's really important that we know what our functional groups are, because they're going to react in a specific way. They're going to have specific chemical and physical properties that'll dictate how they behave in a chemical reaction. So you want to make sure you know your functional groups so that you know where a reaction can occur. The elements that we gain must appear on either the starting material or the reagents. Basically, we're not alchemists, so you need to have all the elements you're going to start with need to be at the product side. Everything that you see in the product had to come from somewhere. So a lot of students will get tripped up on questions where it's asking about the reagents. So it'll be, you have starting materials, you're given a product, and you're asked what the reagents are. Make sure that whatever elements you need in your product are incorporated in that reagent. The elements had to come from somewhere. So if you need hydrogen, make sure that there's a hydrogen in whatever reagent you're picking. And most of our reactions are going to be functional group interconversions, meaning that we're going to be going from one functional group to another. So if you can organize your notes to be based on how do I make an alcohol? How do I make an alkyl halide? How do I make an alkene? And have it based on the different ways of going in between your functional groups, it's going to make your synthesis problems a lot easier. So if you can organize it based on those functional group interconversions, it's going to make life so much easier. All right, so some key terms that we've been throwing around. So nucleophile, we had said that that was going to be our Lewis base. That is the electron-rich species. That is the thing that has electron density. It gets abbreviated as either Nu or NuC. It will react with our electron-poor species, which will be our electrophile. It is going to be said that it will attack because it has the electron, so it'll go first. It'll be where the arrow starts. It goes from the nucleophile to the electrophile. So our nucleophile attacks the electrophile. What we're looking for are the same things that we see with our bases. Negative charges, lone pairs of electrons, pi bonds. These are going to be good indicators of greater concentration of electron density. Those will be good nucleophiles. Your electrophiles, those are our Lewis acids. So we tend to abbreviate them E+ to remind ourselves that it's usually the thing with the positive charge. It's the electron-poor species. So it is the thing that gets attacked by the nucleophile. So we're looking for positive charges or leaving group. Nucleophile literally means nucleus lover. So the nucleus is the positive, whatever, I destroyed the spelling of nucleus. It is the positive charge, the nucleus has a positive charge. So opposite charges attract, so if it loves that positive charge, it itself has a negative charge. Our electrophiles are the electron lovers. So they are the things that are the thing without electrons because they love electrons, so they must be the positive charge because opposite charges attract. Our leaving groups are going to be the group that leaves. It is the functional group that is lost, replaced, or eliminated during a reaction. it is going to be something that'll be stable when it takes that electron density. So we're gonna look for electronegative atoms and anything, especially if it can be neutral after it leaves, anything that'll stabilize that electron density. So these are usually going to be your weak conjugate bases, because your good leaving groups are gonna be poor nucleophiles usually. The really only exceptions are halogens. Halogens get a little tricky. But in general, it's a good leaving group is something that's going to leave, take the electron density, and not want to react, not want to attack anything when it takes that electron density. It just stays happy. It left and it's chill all by itself. That is your good leaving groups. Our nucleophilicity trends are going to be very similar to our base trends, but unfortunately, there's no absolute scale because that would be too easy. So it is still similar to our base trend, but we're going to have some other factors to consider. So I'm going to highlight when we deviate from it. The number one place where our nucleophile deviates from our base trend is sterics. So this bases do not care about sterics because bases are attacking a hydrogen. Hydrogens are really small, so it doesn't matter how big your base is. Nucleophiles, it does, because you need to be able to reach your electrophile. So the better nucleophile will be the thing that is a smaller molecule. So in this case, when I look at my alpha carbon, my primary alcohol is going to be better than my secondary alcohol, which is way better than my tertiary, which we're going to say is not a nucleophile. Because now it has so much baggage that it's bringing along with it. It's kind of like if you've ever flown on a plane and you've seen, so like they have the really narrow aisles to try to get down. And if you've ever seen those people that come in with way more bags than they were supposed to be allowed, so they have like their backpack, an actual carry-on, a personal bag, they went to duty free, so they have actual bags as well, and they're just like swinging down and they're just like hitting people in the face, like that's a bad nucleophile. They are too big. It's a bad passenger. They are not able to easily get to their seat without hitting everything else. They're bumping into the other atoms, the other people. So that is that bad, they are too big to get to their seat at the back of the plane. So that is what's going on with our nucleophiles. Sterics is going to be our number one factor. You have to be small enough to reach your electrophile. That'll be our biggest consideration. And that is what is different to our bases. Our bases don't care. Our nucleophiles do, very much so. Next, we're going to consider charge. This is the exact same thing as bases. The same as our base trend. The reason why the charge matters is because the strength of the new bond. So it still works where that negative is going to be the better nucleophile, which is better than neutral, which is way better than being positively charged. So having that greater concentration of electron density means you're going to end up with a neutral bond when you are, like if you react and you get OMe, oops. So if that attacks something, once it reacts, it becomes neutral. That's going to be a stronger bond than if you make something that now has that polarized, that charge. So having it be a neutral bond in the end is going to lead to a stronger bond. So that is going to be the better nucleophile. That's the same thing as our base trends. That negative charge is going to make you a better base. When we consider our electronegativity, when your electrons are farther from your nucleus, they are going to be more reactive. So you want to have the less electronegative atom. This is again the same as your base trend. For polarizability, as you increase the polarizability, that is increasing your nucleophilicity. So that means that we are decreasing our resonance. So when we look at these examples, the greater the localization of your electron density, the greater that concentration of electron density is on one atom, that is going to make it more reactive, less stable. So then that's going to make it a better nucleophile. So when we're comparing these, we get no resonance. We have resonance structures where this is our major resonance contributor. Then we get equal resonance contributors, and the nitro group is even better because now it's 100% symmetrical. Also, as we increase the size of the atom, then it's going to have a larger electron cloud, so then it's going to have a lower energy for the transition state, meaning it's a lower energy of activation barrier. So larger atom is going to, in general, be the better nucleophile. That is where we deviate from our base trend. That's really significant when we look at our solvent effects. So our base is also not really affected by solvent, but our nucleophiles are going to be extremely affected by solvent. So we're going to have to pay attention to what solvent we are using. What is the medium that makes our reaction real? So solvation is stabilizing our starting material. That means that it's a lower energy for that starting material, and therefore it is less reactive. So solvation is necessary for the reaction to occur. You have to exist in something. But the extent to which you interact with your solvent is going to affect the extent to which you can then interact with your electrophile. So if you, as a nucleophile, interact more with the solvent than you do the electrophile, your reaction is slowed, right? Because you're hanging out with the solvent, you're not actually making it to the electrophile. So that's what we're going to see with our polar protic solvents. Our polar protic solvents are going to be greatly impacted by our solvation because they're going to have a really strong solvent shell. So essentially, if I have a chloride, a small atom, and I get water all around this, I get all of these ion-dipole interactions. I get this shell where this chlorine now can't actually get to my electrophile because it is so tightly interacting with my solvent. That solvent has formed a shell, a protective coating around that nucleophile. So what we see is that this is where the size and polarizability is greatly significant, where our larger atoms will not be as easily solvated. So the larger atoms are not going to have as tight of a solvent shell, so they're going to be better nucleophiles. That's for our polar protic. So that's anything, think like anything that can do hydrogen bonding is going to be a protic solvent. So what we see is that our base size trend flips, where the larger atom is the better nucleophile. Whereas in our aprotic solvent, our not protic solvent, things that can't do that hydrogen bonding, these are going to more directly align with our base trend. Where now the smaller atom is the better nucleophile. Again, because it's going to be less stable with that electron density. So now it becomes the stability of the actual ion that is the greater factor. So aprotic solvents, our nucleophiles and our bases are going to be pretty similar. They'll follow basically the same trends, with steric still being our #1 factor. Our protic solvents, we got to pay attention to atom size, where atom size is going to flip. When we look at our electrophiles are those Lewis acids, those electron lovers. So what we're looking for are the positive charges, incomplete octets. If you have an incomplete octet, then you are going to attack the atom directly. So for example, if I have a carbocation, then you attack that atom directly. If you have a full octet and a positive charge, then you attack the neighboring atom, not the atom with the positive charge itself. So that would be an example of something like this. So this is an oxonium ion. Where that's going to be our leaving group. So our electrophilic atom is the one next door, and it's favorable because that oxygen is going to then be neutral after it leaves. So we attack the neighboring carbon so that the good leaving group can leave with the electron density. So if the atom with the positive charge, ooh, I didn't actually draw my positive charge. Oops. The atom with the positive charge is a full octet, then you attack next door. Our other good electrophiles are empty p orbitals, so our good normal Lewis acids, like aluminum trichloride. Where you get that empty p orbital on that aluminum, or for boron was the same way. That made it a really good Lewis acid because it had a vacancy. It didn't have a full octet, so we could attack that atom directly. And then the other thing was that leaving group. So wherever you see that partial positive, that partial positive is then going to be our good electrophile. That's our electrophilic atom. So the more positive you are, the more of a formal positive you have, the stronger the electrophile. The less partial positive you are, the worse of an electrophile you are. The better the leaving group, the better the electrophile. So when we look at our leaving group qualities, what we're looking for is that electronegative atom. So we're thinking like chlorine, bromine, iodine, oxygen, highly electronegative atoms, or things that can really easily stabilize that negative charge when it leaves, or stabilize that lone pair when it leaves. The best case is going to be where it's neutral after it leaves. So for example, if I'm comparing that oxonium ion to just a normal alcohol, that oxonium ion is the better leaving group because it leaves as with a neutral charge. Whereas if you have an alcohol and that alcohol is acting as your leaving group, then it's going to leave as a hydroxide. Now it has a negative charge that's going to make it more reactive, less stable. Also, if we imagine for our halogens, the weaker conjugate base is going to be the better leaving group. Except if we're in protic solvent. Because our nucleophilicity trend flipped in protic solvent. So the good leaving groups are usually the poor nucleophiles. The halogens are the ones to watch out for, because the halogens can be both a good leaving group and a good nucleophile. And solvent effects are the major factor that are going to determine if it's going to be a good nucleophile or not when it comes to our halogens. Common leaving groups are anything that's neutral after it leaves, so water is a great one. That iodide is usually a really good leaving group as long as you're in a protic solvent. And our sulfonates. So our sulfonates are those groups like this. So your O. Oops. Bless you. I'll have it after it leaves. Okay. So we can have three types of sulfonates where R, well actually there are a bunch of them, but there are three main ones that act as good leaving groups. So if R is a CH3, then we're going to call it a mesylate. And it gets abbreviated MS. And our sulfonate part of it is this part. So if you had let's say you had this thing. That would be abbreviated as OMS. Where the OMS, the whole thing, is the good leaving group. If R is toluene, which is where you have a benzene with a methyl on it, it's called tosylate. Gets abbreviated TS. If R is a CF3 group, then it is a triflate, and it gets abbreviated TF. Our triflates are our best leaving groups. They will never act as a nucleophile. They are exceptional leaving groups. Those are sulfonates. Still very good would be that having ammonia, again, because it's neutral after it leaves. Then our other halogens are also going to be good leaving groups, again, depending on our solvent. Bromine is generally going to be a good leaving group because it's in the middle between iodine and chlorine. Iodine and chlorine are the two to watch out that they can flip sometimes. For our class, we will never use fluorine as a leaving group. Fluoride is very reactive. Even though it is our most electronegative atom, so it does actually want that electron density, it is so small that even though it wants it, it's not going to be happy once it gets it. It's kind of like a small child on Halloween that has a massive amount of candy and is super pumped and then eats all of it and then feels like it's going to throw up. Like, that's fluorine. Fluorine is like, I want it, I want it, I want it, I want it. Oh, I don't feel good. We got to do something about this. I can't handle this electron density. I can't handle this negative charge. I got to react to something else. It is so small that it's just not stable with all of that electron density. So we will never, ever use fluorine as a leaving group. It's a bad leaving group. Hydroxide, we will only use as a leaving group if you have an oxide as a reactant. So if you already start with O-, then you can make O-. So if you have hydroxide as a base, then you can have hydroxide also come off. It's still not good, but it works. So we will only have hydroxide if we're already making oxides in solution. If you already start with O-, then you can make O-. But in general, we're not going to have oxygen. We're not going to make hydroxide because hydroxide, like it's a strong base. So that means that it's going to be a reactive reagent. So it's going to be a bad leaving group because it's not stable, right? Okay. So for, say, this upcoming quiz, how can we be expected to know how to use this information? So something like this would be a good example of, say, we're matching our label of addition, substitution, or elimination to our reaction. So is this one going to be addition, substitution, or elimination? Let's review what those three are. All right, so do we remember what substitution is? You're substituting your functional group. So it's where you go from one functional group to another functional group. You substitute your functional groups. Elimination is where we are eliminating a leaving group. So it's going to be no pi bond to pi bond. Addition is the opposite of our elimination. That's where we go from pi bond to no pi bond, or fewer. Right? So then what is this first one going to be? It is addition, because I go from pi bond to no pi bond, so that is addition. How about the next one? Substitution. I'm going from my haloalkane to an alcohol. That is substitution. All right. How about this next one? Addition. I'm going from those pi bonds to no pi bonds. Looking at the same carbon atoms is where I'm seeing that change. All right, how about this last one? Elimination. I'm going from no pi bond to pi bond. Cool, straightforward. Those are the general reaction trends. All right. Next thing you'll be expected to be able to do is identify your nucleophilic atom, electrophilic atom, and your leaving groups. So when we look at this example, I find it easiest to find the leaving group because it is the group that is no longer attached to my carbons. So what is my leaving group? Bromine. So bromine wasn't drawn in, but it still existed. That bromine is my leaving group because it is no longer attached to my carbon scaffold in the end. And we care about carbons in this class, so we're looking at that carbons. Your electrophile will be the molecule with the leaving group. So what is my electrophile? 2-bromopropane. That thing, this whole thing is now my electrophile. So if that's my my electrophile, what's my nucleophile? What else is in solution? Yeah, the OH, the hydroxide. So the whole molecule is my electrophile. That hydroxide is my nucleophile. You can say sodium hydroxide is your nucleophile. But the question is asking about my nucleophilic atom and my electrophilic atom. So when I look at this, on my electrophile, I now need to find the most positively charged atom. So which one is my electrophilic atom? Yeah, the carbon in the middle, the carbon with the bromine, the carbon with the leaving group. That is my electrophilic atom. What is my nucleophilic atom? Yeah, the oxygen. That oxygen is your nucleophilic atom because it's the one with the greatest concentration of electron density. You also can recognize that your carbon had to be your electrophilic atom because that's what your nucleophile is directly attached to. You made the oxygen-carbon bond, and we're going to go from nucleophile to electrophile. You're going to go from the nucleophilic atom to the electrophilic atom, so that reinforces that, yep, we did it correctly, because my nucleophilic atom and my electrophilic atom are now connected. Cool. I want you to reference these trends throughout the entire semester. Keep these in mind. It'll make your life so much easier. There won't be as much memorization because you'll start to see the trends and it'll start to feel very repetitive. If you ever feel like you're getting bogged down and overwhelmed, that's when you want to look back at this and try to take a step back from all the details and just look at what are the trends again. What are the overarching themes that I can start to see the patterns in it? And then that'll make life a little bit easier. All right. Are there any questions about that? Yes. Sure. So to assign your nucleophilic site and your electrophilic site, you have to do it step by step. So we're going to do it for the first step, and then we'll reassess. So what is my nucleophile? What is my electrophile? So it's going to be the reactants. What has electrons, what doesn't? First of all, do we have a leaving group? No. So our addition reactions are a little different. For substitution elimination, both of those will have leaving groups. Addition reactions are not going to have leaving groups. So we can't use leaving group as our indicator for electrophile and nucleophile. What is HCl? Hydrochloric acid. So it's a strong acid. So what is it going to act as? An acid, yeah. So then which one, nucleophile or electrophile, is associated with acids? Electrophile. Think of it as H+. Remember, it dissociates into H+ and Cl-, like it dissociates. It's the H+ that is that reactive part initially. So that is the electrophile, is the positive charge. So what does that make our alkene? The nucleophile. The pi bond is going to be the nucleophilic site because I don't see any lone pairs, I don't see any negative charges. If you're asked for a nucleophilic atom, you just have to say carbon because that's the element that's going to end up attached to the hydrogen. All right, so then your electrophilic atom would be the hydrogen initially. Nucleophilic atom, I guess, would have to be carbon, or you would say the pi bond is the nucleophilic site. All right, so then that's the first one. So now we're going to do the next one. Now we reassess. These are the products of that step. So now, nucleophile, electrophile. What has electrons, what doesn't? Thank you. What'd you say again? Sorry. So the Cl- is not the electrophile. So what's that make it? Nucleophile, cool. So remember, nucleophile is nucleus lover. So it wants the positive charge. It doesn't have the positive charge. So the nucleophile is the thing with the negative charge. So that's going to be our chloride. So then our electrophile, the electron lover, is the thing without electrons. So that is the carbocation. So our nucleophilic atom is going to be that chlorine. Our electrophilic atom is the carbon with the positive charge. Because that carbon does not have a full octet, so we attack it directly. It gets reinforced by the fact that that carbon and that chlorine are directly connected to each other. Also, just to make sure that we see it, this hydrogen is attached here. That's where that hydrogen ended up. Because you started with only 2 hydrogens, and now you have 3. So that's how we would do nucleophile, electrophile for addition reactions. There's no leaving group, so it's a little bit harder. Cool? Yeah. So the way it's drawn is favored. The reason why is because if you put hydrogen in the middle and the positive charge on the end, that makes a primary carbocation versus secondary carbocation. Secondary is more stable than primary because of our induction and hyperconjugation. So for that reason, we're only going to make the carbocation in the middle, so then chlorine only goes to the middle. That'll be on the final exam. I mean, it will. We'll cover that eventually. We'll do addition reactions after exam 2. All right. Any other questions? Okay. All right. Then let's talk about our substitution reactions. So our substitution reactions, this is where we are exchanging one group for another. All substitution reactions are going to have a nucleophile, that'll be the thing that displaces the leaving group, an electrophile, that's our substrate, is the thing with the leaving group, and a leaving group that's attached to our substrate. So our general reaction is where we see nucleophile is going to be attacking our electrophile, the thing with the leaving group, to give us that nucleophile carbon bond and leaving group has left. So that's the general reaction. So all of our substitution reactions are going to look really similar in terms of the products that are formed. We have 2 main types of mechanisms. There are more than 2. We're only going to focus on 2 this semester. We have SN2 and SN1. These are the how. So the what is that substitution. That's what we're doing. That's the product that we're making. How do we do it is the mechanism. Those are the curved arrows actually illustrating how we make those products. And so we have two options. We have SN2 and SN1. SN2 is a bimolecular nucleophilic substitution. Why it's almost in reverse order, I don't know. But the 2 is for the bimolecular, nucleophilic for the N, S for substitution. This is one step. SN2, one step. SN2 has the 2 because there are 2 reagents in the rate determining step. So the 2 is telling us the number of molecules in the rate determining step, which is going to be our nucleophile and the electrophile, because they're both going to be reacting together at the same time. We're only going to have one step. That will be our slow step because we have one step. It's also our fast step, but we normally don't care about fast steps. We care about slow steps. So it's going to be where the leaving group leaves as the nucleophile attacks. That's what's happening. So for our SN2 reaction, what that looks like is you have your nucleophile, you have, I'm going to abbreviate NU, and then you get your leaving group with your electrophile. So it's going to be nucleophiles attacking and leaving group is leaving all in one step. Your nucleophile is essentially pushing out your leaving group. So it's going to be where we have the really reactive nucleophiles. We are making that nucleophile carbon bond and breaking the carbon leaving group bond simultaneously at the same time. That is SN2. SN2, one step, because there are 2 reagents in that step being used, 2 molecules coming together simultaneously. SN1, on the other hand, is our unimolecular nucleophilic substitution. SN1, 2 steps. SN1 is a 1 because there is 1 molecule in the rate determining step. So again, that 1, the number, tells us the number of molecules in the rate determining step. In this case, it'll be just the electrophile. Just the substrate is in the slow step. So what we're going to see is that it's going to be leaving group leaves, then nucleophile attacks. So SN2, one step, leaving group leave as nucleophile attacks. SN1, 2 steps, leaving group leaves, then nucleophile attacks. 1 reagent in the slow step, 1 reagent in the rate determining step. So what we're going to see is that we have first leaving group leaves. We're going to generate a carbocation intermediate. And then the nucleophile will attack. So SN1, 2 steps, leaving group leaves, then nucleophile attacks. You're going to make a carbocation intermediate with SN1. You will not have carbocations with SN2. How many steps are in SN2? 1 step. How many steps are in SN1? 2 steps. Good. What are the steps of SN2? The leaving group leaves as the nucleophile attacks. What are the 2 steps of SN1? Leaving group leaves and then the nucleophile attacks. All right. So we're going to look at SN2 first in greater detail, and then we'll go to SN1, and we'll do just, yeah, that'll be the order we go through. So when we look at SN2, our rate equation is where we have K, which is just some rate constant, and it is impacted by the concentration of both the substrate, your electrophile, and the concentration of your nucleophile. The rate depends on both the substrate and the nucleophile. That's why it's SN2, because you have two things in your slow step. When we look at a potential energy diagram, it is one step for that SN2. So we get one transition state for the SN2 reaction. Our transition state, if we imagine that this is the nucleophile, and we have that, again, that generic electrophile. So then our product is where we have nucleophile attached to the carbon and leaving group left. When we look at our transition state, we're going to see that we have the partial bond being made between the nucleophile and the carbon. And the partial bond being broken between the carbon and the leaving group. When we use our Hammond postulate, we can now predict the relative charges. So if we assume our nucleophile initially was negatively charged, well, I guess let me start here. Is this reaction endothermic or exothermic? Exo, because it's given. We see that our products are lower in energy than our starting materials. So for an exothermic SN2, which most of them will be exothermic, for this exothermic, that means that it's going to be an early or a late transition state. Early, because it looks more like the starting materials. So then, where do I put a partial charge? Do I put a partial charge on the nucleophile or the leaving group? The nucleophile, because in this example, I need to look more like my starting materials. So I don't care what the products look like. I look more like my starting materials. I see a negative charge on the nucleophile, so I put a partial negative in the transition state. All right, if I'm going to do long and short bonds, is that carbon nucleophile bond long or short? Long. Because it doesn't exist yet in the starting materials. If you don't see the bond, then it's long. If you do see the bond, then it's short. So how about that carbon leaving group bond? Long or short? Short. Good. That's how we apply the Hammond postulate from last class. When we look at our energy diagram, that's how we can figure it out to know what our transition state needs to look like. So we are seeing that we are making the carbon nucleophile bond and breaking the carbon leaving group bond simultaneously. That is our transition state. We're going to be able to affect the rate of our SN2 reaction by looking at both the nucleophile and the substrate, because both of them are involved in the rate determining step. So the nucleophile, we're going to look at its strength factors. And then for our substrate, we're going to have both the substrate structure as well as leaving group ability. We're going to have both of those combined to have our three ways we're going to affect it. But first, we're going to look at the stereochemistry of our SN2 reaction. Our SN2 reaction is going to always occur through backside attack. So it's going to be where we are attacking the backside of the leaving group. We're coming from the carbon on the opposite side of that leaving group. So that means that R goes to S, S goes to R, usually, not always. So if we assume that the nucleophile is number 1, That's how we're seeing that flipped inversion. All right, so next class we'll look at why this happens, and we'll keep going through the rest of our reactions. All right, have a wonderful day.